This is the lecture for section 2.3, the structure of z sub p when p is prime, and z sub n. So we'll first look at the case when p is prime. As seen in the previous section, not all the properties of z necessarily hold in z sub n. For instance, the zero factor property holds in z sub 5, but not in z sub 6. The problem arises because 6 is composite. The first theorem below shows that as long as the modulus is prime, then the zero factor property will hold in z sub n. In the case that the modulus is prime, z sub n has some additional properties that do not hold even in z. For instance, when a is not equal to 0, the equation ax equal 1 has a solution in z if and only if a is plus or minus 1. The multiplication table for z sub 5, however, shows that for any class of a not equal to the 0 class, the equation a times x equal the class of 1 has a solution in z sub 5. For example, x equal 3 is a solution of the equation 2 times x equals 1 in z sub 5. And x equal 4 is a solution of the equation 4 times x equal 1 in z sub 5. In fact, this same result holds whenever the modulus is prime. So we want to examine theorem 2.8. So this says let p greater than 1 be an integer. Then the following conditions are equivalent. The first condition is that p is prime. The second condition is the existence of multiplicative inverses. And what this says is for any class of a not equal to the 0 class in z sub p, the equation a times x equal 1 has a solution in z sub p. That is, for any a not equal to 0 in z sub p, there exists an element x equal u in z sub p such that a times u is equal to 1. The element u is a multiplicative inverse of a. And then property 3 is the zero factor property, which states for all ab in z sub p, if a times b is equal to 0, then a is 0 or b is 0. So the product of two classes is 0 implies that one or the other of the two classes must be equal to 0. Now before we start the proof, just a remark about this type of theorem. So in this theorem we have three conditions stated to be equivalent, which means each condition holds if and only if each of the other two holds. To prove a theorem like this, we can show that condition 1 holds if and only if 2 holds, 2 holds if and only if 3 holds, and 3 holds if and only if 1 holds. This would involve proving 3 biconditional statements for a total of 6 separate proofs. Alternatively, we can prove condition 1 implies condition 2, 2 implies 3, and 3 implies 1. Proving these 3 conditional statements will suffice to show each condition implies each of the other two. For instance, if we know that 1 implies 2 and 2 implies 3, then it follows that 1 implies 3. In a similar manner, we can show each statement implies the other two. Another remark is, in order to prove results involving z sub n, there are two basic approaches. So the first is to translate the equations in z sub n into equivalent congruence statements in z, then apply the properties of congruence and arithmetic in z. The second approach is to use the arithmetic properties of z sub n directly without involving arithmetic in z. So we'll see how to apply each of these two techniques in the proof of the theorem. So now we're ready to dive into the proof. So we'll start with 1 implies 2. So we'll suppose 1, namely that p is prime, and we need to show condition 2. For any a not equal to 0 in z sub p, there exists an element x equal u in z sub p such that a times u is equal to 1. So let's suppose that a is an arbitrary element in z sub p with a not equal to 0. We need to show that there exists an element x equal u in z sub p such that a times u is equal to 1. We'll use the first approach described above. So since a is not equal to 0, then by theorem 2.3, a is not congruent to 0 mod p. This implies that p does not divide into a. Let's consider the GCD of A and P. Now, since this must divide P, and P is a prime, then the GCD either equals 1 or P. Now, since the GCD of A and P also divides A, and we're supposing that P does not divide A, then the GCD of A and P must be equal to 1. Now, by theorem 1.2, since the GCD is 1, there exist integers u and v such that AU plus PV is equal to 1. So we can write the GCD, which is equal to 1, as a linear combination of A and P. So then AU minus 1 will be equal to P times minus V, which implies that P divides AU minus 1, so that AU is congruent to 1 mod P. Then, translating this back into an equation in Z sub P, we obtain the class of AU is equal to the class of 1, and this is equivalent to the class of A times the class of U is equal to the class of 1. And so if we choose X to be the class of U, then X equal the class of U is an element of Z sub P which satisfies the required condition, which proves condition 2 holds. Next, we'll prove 2 implies 3. So we'll suppose that 2 is true, and we need to show 3 for all classes A and B in Z sub P if the class of A times the class of B equals the class of 0, then the class of A is 0 or the class of B is 0. Now this has symbolic form as shown for all A, B, and Z sub P. A times B equals 0 implies A equals 0 or B is equal to 0. So the symbolic form is a conditional statement with an or in the conclusion. Now, typically, when you're trying to prove a statement that has this type of symbolic form, we use this equivalence. So the equivalence states that P implies Q or R is logically equivalent to P and not Q implies R. This is where P, Q, and R are any statements. So we see that the statement we're trying to prove will be logically equivalent to the statement for all A and B in Z sub P. A times B is 0, and A is not equal to 0 implies B is 0. So to prove this, we'll use the second approach described above and work with the properties of Z sub P directly. So we'll suppose that A and B are arbitrary elements of Z sub P. We'll suppose our hypothesis that A times B is 0 and A is not equal to 0. And we then need to show the conclusion that B is equal to 0. Now, since A is not equal to 0, then it follows from condition 2, which we're supposing is true, that there exists an element X equal U in Z sub P such that A times U is equal to 1. So then, multiplying both sides of our equation A times B equals 0 by U, we obtain U times the quantity A times B is equal to U times 0. Now we want to use the properties of Z sub P that were proved in the previous section. So we know, for instance, that the multiplication in Z sub P is associative. So on the left side of this equation, we can rearrange the parentheses and we obtain the quantity U times A times B, and on the right side, U times 0 by the definition of multiplication in Z sub P will be the class of U times 0. Okay, now the multiplication in Z sub P is also commutative, so on the left side, the product U times A is the same as the product A times U. And on the right side, we can replace the U times 0 with just 0. So we obtain the class of 0. Okay, now on the left-hand side, A times U, the quantity in parentheses, is equal to the class of 1. So on the left side, we'll have the class of 1 times the class of B is equal to, on the right side, the class of 0. And then the class of 1 times the class of B is just the class of B. So this shows that the class of B is 0, which is what we needed to show. And so this proves the equivalent statement, so proves condition 3. Next, and finally, we have condition 3 implies condition 1. So we'll suppose 3 holds, and we need to show 1 holds, that P is prime. So to show that p is prime, we could, using the definition, show the only divisors of p are plus or minus 1 and plus or minus p. Alternatively, we can use theorem 1.5. According to this theorem, to show that p is prime, we can show that it satisfies the condition for all integers b and c, p divides the product bc implies p divides b or p divides c. According to theorem 1.5, an integer p is prime if and only if it satisfies this condition. So to show that it satisfies this condition, we'll suppose that b and c are arbitrary integers. We'll suppose the hypothesis that p divides the product bc, and we need to show the conclusion that p divides b or p divides c. Now, since p divides bc, that tells us that bc is congruent to 0 mod p. By theorem 2.3, this implies that the class of bc is equal to the class of 0 in z sub p. So converting from our congruence relation to congruence classes, we obtain this result. And this is equivalent to the class of b times the class of c equals the class of 0 in z sub p. Now by condition 3, the zero factor property, bc equals 0 implies that either b is 0 or c is 0. And translating back into congruence, it follows that b is congruent to 0 mod p or c is congruent to 0 mod p. And this implies p divides b or p divides c, which is what we are trying to show. And thus p is prime, which proves condition 1. And this completes the proof of the theorem. We've shown 1 implies 2, 2 implies 3, and 3 implies 1. Now before we proceed with some examples and additional results, we want to introduce some new notation. And so far we've been using the notation A enclosed in brackets for the congruence class of A in Z sub n, and the notation circle plus and circle dot for the addition and multiplication of the congruence classes in Z sub n. Ordinarily, we drop the special notations and we would just use A in place of A enclosed in brackets, and just an ordinary plus sign in place of the circle plus sign, and an ordinary multiplication symbol, a dot, in place of the circle dot, provided the context is clear. So if we know that we're dealing with congruence classes and not integers, we can drop the bracket notation and we can drop the circles around our operations. Now, for instance, if we're working in Z sub 5, we can write 4 plus 1 equals 0 for the class of 4 plus the class of 1 equals the class of 0. And 3 times 4 equals 2 for the class of 3 times the class of 4 equals the class of 2. Now, dropping the bracket notation for elements of Z sub n, we can rewrite the second and third parts of the previous theorem as follows. So condition 2, we'll write it as condition 2 prime, will state for any a not equal to 0 in Z sub p, the equation ax equals 1 has a solution in Z sub p. So you have to keep in mind here, since a is in Z sub p, that it's really a congruence class and not an integer. That is, for any a not equal to 0 in Z sub p, there exists an element x in u, x equals u in Z sub p, such that a times u is equal to 1. And then condition 3 prime, the zero factor property, states for all ab in Z sub p, if a times b is 0, then a is 0 or b is 0. Next, we want to talk about the structure of Z sub n. So this is for general n, not necessarily in the case where our modulus is prime. Now, theorem 2.8 tells us that when p is prime, then the equation a times x equal 1 has a solution in Z sub p for all a not equal to 0. When n is not prime, however, the equation ax equal 1 may or may not have a solution in Z sub n. For an example, we can show that the equation 2 times x equals 1 does not have a solution in Z sub 8, but 3 times x equal 1 does. So using exhaustion, we can verify that 2 times x equal 1 does not have a solution in Z sub 8. So 2 times 0 is equal to 0, so that tells us that 0 is not a solution. 2 times 1 is equal to 2, so that tells us that 2 is not a solution. 2 times 2 is 4, so that tells us that 2 is not a solution. 2 times 3 is 6, so 3 is not a solution. 2 times 4 is 0, so 4 is not a solution. 2 times 5 is 2, so 5 is not a solution. 2 times 6 is 4, so 6 is not a solution. And 2 times 7 is 6, so that 7 is not a solution. So therefore, the equation 2 times x equal 1 does not have a solution in z sub 8. None of the elements in z sub 8 satisfy that equation. However, if we look at the equation 3 times x equal 1, well, 3 times 3 is equal to 9, the class of 9, which is equal to the class of 1. So that tells us that 3 times x equal 1 does have a solution, namely 3. Now the next result tells us exactly when the equation a times x equal 1 does have a solution in z sub n. So this is theorem 2.9. And this says, for all integers a and n with n greater than 1, the equation a times x equal 1 has a solution in z sub n if and only if the GCD of a and n is equal to 1 in z. So the equation now involves congruence classes, but you have to keep in mind that a and n are both integers. So for the proof, well, let's suppose that a and n are arbitrary integers with n greater than 1. We need to show the statement in the condition in the theorem that a times the class of a times x equal the class of 1 has a solution in z sub n if and only if the GCD of a and n is equal to 1 in z. So this is a biconditional statement, so we need to prove the forward and backward directions. So for the forward direction, we'll suppose that the class of a times x equal the class of 1 has a solution in z sub n. So let's say our solution is x equal the class of u. And we need to show the conclusion that the GCD of a and n is equal to 1. Now the hypothesis implies that the class of au is equal to the class of 1 in z sub n, which implies that au is congruent to 1 mod n. So that implies that n divides au minus 1, which implies that there exists an integer k such that au minus 1 is equal to kn. So then au minus kn is equal to 1. Now, by an exercise in section 1.2, since this is a linear combination of a and n which equals 1, that tells us that the GCD of a and n is equal to 1. And this proves the forward direction. Okay, so the exercise now is the converse of theorem 1.2 in the special case that the linear combination equals 1. So theorem 1.2 says that the GCD can always be written as a linear combination of the two integers, and the converse of that would say if the GCD can be written as a linear combination of the two integers, or if an integer can be written as a linear combination of the two integers, then that integer must be equal to the GCD. And that converse only holds in the case that the linear combination equals 1. It doesn't hold in general. Okay, now we have the backward direction. So we're going to suppose that the GCD of a and n is equal to 1 in z. And we need to show that the class of a times x equal the class of 1 has a solution in z sub n. Now, since the GCD of a and n is equal to 1 in z, then by theorem 1.2 there exists integers u and v such that au plus nv is equal to 1. So then au minus 1 is equal to nv, which implies that au is congruent to 1 mod n. And this implies that the class of a times the class of u is equal to the class of 1 in z sub n. And therefore x equal the class of u is a solution to the equation class of a times x equals the class of 1 in z sub n. So this proves the backward direction, and this completes the proof of the theorem. So next we want to talk about units and zero divisors. So we want to introduce some special terminology when dealing with this equation, a times x equals 1. And so our definition, let n be a positive integer. An element a in z sub n is a unit, provided that the equation ax equal 1 has a solution. So that is, a is a unit provided that there exists an element b in z sub n for which a times b is equal to 1. In this case, we say that b is the multiplicative inverse of a, and multiplicative is in parentheses because we can generally omit it, and if we just say that b is the inverse of a, it's understood to be the multiplicative inverse of a. Note that ab equals 1 implies that ba equals 1, which implies that b is also a unit with inverse a. So in the case that a is a unit with inverse b, b is a unit with inverse a. So the relationship is reciprocated. Now it follows from theorem 2.8 that when p is prime, every non-zero element of z sub p is a unit. So theorem 2.8 said that in the case that p is prime, then the equation a times x equals 1 always has a solution for non-zero elements. Now theorem 2.9 can be restated in the terminology of units. So we'll restate this as theorem 2.10. So for all integers a and n with n greater than 1, the class of a is a unit in z sub n if and only if the GCD of a and n is equal to 1 in z. For an example, we can find all the units in Z15. For each unit, we want to find its inverse. Now, according to theorem 2.10, the class of a in Z sub 15 is a unit if and only if the GCD of a and 15 is equal to 1. So it follows that the units will be the class of 1, the class of 2, the class of 4, the class of 7, the class of 8, the class of 11, the class of 13, and the class of 14. These will be all the elements in Z sub 15 which are relatively whose class representative is relatively prime to 15. And we can use exhaustion to find the inverses. So we can just try, or trial and error. So 1 times 1 is equal to 1. So that tells us that 1 is its own inverse. 2 times 8 is 16, which is equal to 1. So 2 and 8 are inverses of one another. 4 times 4 is equal to 16, which is equal to 1. So 4 is its own inverse. 7 times 13 is 91, which is equal to 1. So 7 and 13 are inverses of one another. 11 times 11 is 121, which is equal to 1. So 11 is its own inverse. And finally, 14 times 14 is 196, which is equal to 1. So 14 is its own inverse. Now we saw in the previous section that the zero factor property, which holds in Z, does not necessarily hold in Z sub n. For instance, in Z6, 2 times 3 is equal to 0, but 2 is not equal to 0 and 3 is not equal to 0. Okay, so now here you have to keep in mind we're talking about elements in Z sub 6, so these are all intended to be congruence classes. So this is really saying the congruence class of 2 times the congruence class of 3 is equal to the congruence class of 0. So for another definition, let's let n be a positive integer. Then a non-zero element a in Z sub n is a zero divisor, provided that there exists a non-zero element b in Z sub n for which a times b is 0. Now, since a times b equals 0 implies b times a is equal to 0, then b is also a zero divisor. So a is a zero divisor means you can find a b for which ab equals 0, and that's going to necessarily imply that b is a zero divisor. Now it follows from theorem 2.9 that when p is prime, the zero factor property holds in Z sub p, which means there are no zero divisors in Z sub p. Now the proof of the following remark is one of the homework exercises. And so the first part says that if the class of A is a unit in Z sub n, then the class of A is not a zero divisor. And 2 says that if the class of A is a zero divisor in Z sub n, then the class of A is not a unit. Now you'll see that condition 2, or property 2, is really just the contrapositive of condition 1, or property 1. So to prove this, we only have to prove 1 or 2. Then the other we obtain by just referring to the contrapositive. For an example, let's find all the zero divisors in Z15. Now from the example above, we found the units in Z sub 15 are 1, 2, 4, 7, 8, 11, 13, and 14. And by the remark, none of the units can be zero divisors. So the only elements that can be zero divisors are going to be the remaining non-zero elements, which will be 3, 5, 6, 9, 10, and 12. And each of these is indeed a zero divisor, as we can see from the following calculations. So 3 times 5 is 15, which is equal to 0. So this shows that 3 and 5 are zero divisors. 6 times 5 is equal to 0. That's 30, which is equal to 0. And that shows that 6 and 5 are zero divisors. Well, we already know that 5 is a zero divisor. And then 9 times 5 is 45, which is 0. So this shows that 9 is a zero divisor. 10 times 3 is 30, which is equal to 0. So this shows that 10 is a zero divisor. And 12 times 5 is equal to 0. So this shows that 12 is a zero divisor. So each of those elements, 3, 5, 6, 9, 10, and 12, are zero divisors.